So last time we started a topic of continuous random variables, and as we discussed a lot of variables, a lot of measures around in economics and in some other fields are possible to model as continuous random variables. Why? Because mostly when we measure something like time, distance, amount of money, stock return, something else, usually when this is related to money, when this is related to, well, time, another measurement like volume, distance, whatever, space, the appropriate way to model is the continuous random variable. Why? Because for discrete random variables, it is useful when you have several few possible values of this random variable, right? 3, 4, 10, something like that. But when we speak about, let's say, amount of money, or when we speak about stock return, the number of possible outcomes for this variable might be very huge. So suppose that you want to call to a person and ask for an income, let's say, of this person. So now there is a census in Russia happening, right? So people need to provide some information. And then suppose that you are a person who, maybe some of you is actually busy with that. Usually students are participating in this national census and they are kind of going to people and asking them this question. So suppose that you want to ask a person about the income of this person. Now, the question is, how many possible outcomes of this variable you can get potentially? I think infinitely many, right? Because so income might be from 0 to, I don't know, to very huge amount. This is the first thing. So the second thing, that differences in this income might be also very small, but still the income is different. So for example, when the person says, well, my income is 50,000 rubles and my income is 50,001 ruble, these are two different incomes. And it's very hard to model such variables in a form of discrete variables. So that's why we use this continuous case. And I showed you last lecture how it works with the stock return when we have a lot of possible outcomes, and then it's not very, let's say, handy to work with the discrete case. So, and the most the important object to characterize this continuous random variable is the cumulative distribution function. So we spoke about CDF before when we spoke about discrete random variables. So now it's exactly the same. It's a probability that our random variable is going to be less than or equal to some given value. So that's an important thing. So we characterize a probability of inequality. Why? Because for continuous random variable, if we want to use the definition of a probability, where was it? So this one, this sum is going to be infinite, and if the sum is going to be infinite, so the number of possible cases is also infinite. And when we want to calculate the probability of one outcome, it's going to be 1 over infinity, so it's almost 0, right? That's why we don't use something similar to probability mass function first for the continuous random variables. We start with these inequalities. So for us, it's appropriate to measure probability that our continuous random variable is going to be in some interval from -infinity to small x. So it must be defined for all real numbers. It has the following properties. We spoke about it. And if you speak about discrete random variables, so it's a step function. from the, let's say, pre-last lecture. And for the continuous random variable, it's continuous by definition, because we define a continuous random variable as a variable that has a continuous cumulative distribution function. So here are two graphs. One is a graph of a discrete random variable CDF, another is a graph for a continuous random variable CDF. So you had this on your exercise sessions, so I hope that you are familiar to this. But this object is going to be used from now on through the whole course of probability, then the next semester through the course of mathematical statistics, and then through the next semester through the course of econometrics. We will be using CDF a lot. So that's why it would be nice to understand, for you to understand this object and what it means exactly. So once again, the meaning is very simple. Our random variable, so it's a probability that our random variable is going to be less than or equal to a given number. For example, when you call to a person to ask a monthly salary of this person, what is the probability that his or her salary is going to be less than or equal to 50,000 rubles? Something like that. So from 0 to 50,000, right? Or what is the probability that the income is going to be less than or equal to 100,000 rubles per month, right? So from 0 to 100,000. That's exactly what CDF characterizes. And I hope you understand that probability of salary being less than 50,000 is not less than probability of a salary being less than 100,000, right? Because 100,000 is wider interval than 50,000. And then using CDF, we do the reverse thing. So still we want to have some analog of probability mass function from discrete random variable. So that's why we are taking derivative of CDF with respect to x in order to obtain a function that is called a probability density function. So probability density function is an analog of probability mass function for discrete case. But once again, it is not the same completely, because probability that random variable, that continuous random variable equals to some number is always 0. It's not possible to calculate this probability. So for this density function, it's always non-negative. So it's either 0 or positive for any x from minus infinity to plus infinity. And the integral from minus infinity to plus infinity for this density function is 1. And this is, so let me open the lecture number 5 for discrete case. This is exactly the same as this property for probability mass function in the discrete case. Why? Because when you sum over all probabilities, you must have 1. So the sum of probabilities must be equal to 1. So then we establish the relationship between PDF and CDF. Basically, if we have a graph of a probability density function, then the area under this graph up to a given value, let's say y0, this area is exactly cumulative density function. We are going to use this concept of area under the curve of PDF a lot in the future, and also you need to be somehow familiar that this area represents a probability. So we went through some examples, started with the example that we have some unknown probability density function with a known coefficient, and then we needed to calculate this coefficient in order to make this PDF a valid density function. And in this case, this number is calculated based on the property that the integral of this cumulative of this probability density function from minus infinity to plus infinity must be 1. So in order to work with continuous random variables, you also need to be familiar to some extent with integrals. And then we calculated this integral, and from this simple equation, we calculated that c is 3/8. So I guess we stop somewhere here, if I'm not wrong. Yes, so that was the material covered on the last lecture. We stopped here with the calculation of c. Now, any questions, anything you want to clarify regarding this part of material? So to wrap up, the most important things: continuous random variable is the random variable that has a continuous cumulative density function. Cumulative density function represents a probability that our variable is less than or equal to some number, so from minus infinity to this number. PDF is the derivative of CDF, and and PDF must be integrated to 1 when we integrate this PDF from minus infinity to plus infinity for all values of x. Okay, so then let's continue. So this is an example of cumulative density function for a continuous random variable. So usually this is an example how properly you need to represent CDF. You need to define this function for all possible values of a random variable. So look, if y is less than 0, then our CDF is 0. If y is from 0 to 1 including, then our CDF is simply y, and when y is greater than 1, it must be 1. So why these two things? Because it's a probability. Probability cannot be less than 0. Probability cannot be greater than 1. This is the first thing. So this 0 and this 1, they are not by chance here. They are they are here by rule. That's the first thing. The second thing is that CDF must be, where is that? Yes, it was here. It must be non-decreasing function. So it must be either constant or increasing, right? So it cannot go down. And if you want to plot a graph of this function, so we have something like this. It's a horizontal line from minus infinity to 0, then it increases. So it's 45-degree line from 0 to 1, and then it's also constant for this interval. Just one example of CDF. If we consider the previous example, and if you want to calculate the PDF for this random variable y, so because the probability density function is the derivative of the cumulative distribution function when the derivative exists, so we take derivative of this function at each interval. And basically for y less than 0, derivative of 0 is 0. For y between 0 and 1, derivative of y is 1. And for y greater than 1, derivative of 1 is also 0. So probability density function is 0 for this interval, it's 1 for this interval, and 0 for this interval. So the graph is going to be like this. And now look, I said that there is also a geometric interpretation of cumulative distribution function of the previous one. This is the area under the graph of PDF. Look, we have something like a rectangle here, right? With the base of 1 and with the height of 1 as well. So the area of this rectangle is 1. And this area 1 exactly coincides with the value of CDF when we evaluate the CDF at y equals 1. For example, if we evaluate this CDF at 1/2, it's gonna be 1/2, right? Because it's just y, 1/2 here. And if we put 1/2 here and we evaluate the area of this under this curve from 0 to 1/2, we will get 1/2 as well. So that's the link between graph of PDF and the value of CDF. Once again, the value of CDF is simply the area under the curve of PDF, or under the graph of PDF, when we evaluate this area from -infinity to a given value of y. So more on this you will do on the exercise sessions. You will look what is the relationship between these two functions. So now some important expressions for continuous random variables. We are going to use these expressions a lot from this point. Now, first of all, when we want to calculate the probability that the random variable is between two values, between a and b, for example. So this probability is calculated as an integral of PDF with these limits of integration from b to a here. So it's something similar to the definition of CDF itself. So probability that x equals c. Knowing this, if we plug as the limits of integration, if you plug c and c here to the integral, we know that this integral is going to be 0. Why? Because the area under the curve and when the base is 0 is going to be 0. The area of a line is 0. So that's why I said that for continuous random variable, there is no probability that this continuous random variable equals exactly to some number. We need always some interval like this. So this interval might be very small, but still there must be interval and not the exact quality. So then, given these two properties, given the first property and the second property, now, is there any difference between strict inequality and weak inequality? No. Why? Because if we, for example, compare these two cases, so probability that x is less than a, greater than a and less than b, and this one, probability that x is less than b and greater than or equal to a. So what's the difference between them? So this probability includes this probability and probability that x equals a. Right? So here we have one additional term, probability that x equals a. But probability that x equals a is 0. So that's why these two are equal. So based on the same logic, we can continue proving this. So here, probability that x is greater than a and less than or equal to b is this probability plus probability that x equals to b. Probability that x equals to b is 0. That's why this and these probabilities are equal. And also here. So therefore, actually, there is no mistake if you write strict inequality, if you write weak inequality, both work. In the continuous random variable case, both work. Of course, if you do discrete case, it doesn't work, because for discrete case, this probability is non-zero, and then you may fail with your logic if you kind of substitute weak inequality with a strict inequality. For continuous random variable, it doesn't matter. So this is just a reminder. We define CDF of a function, of a random variable, sorry, as the probability that x is less than or equal to some value, small x. And now, given this, and given these inequalities, we can redefine this probability in the following way. Look, oh, there are two things. Okay, so first of all, what is CDF in terms of integrals? Look, if you consider this probability and how we define this probability with the help of PDF, and if you look at this inequality, so what's the difference? On the left hand side, we have minus infinity, right? So here, instead of a, we have minus infinity, and instead of b, we have this small x. So therefore, we can define CDF as an integral of PDF from minus infinity to small x. So t is just a variable of integration. So we use t here. I can use y, z, whatever. Why we change this variable? Because x now is in the upper border of integration. So that's why I cannot use x here and here, because it's going to be kind of nonsense. And now, using this knowledge we can define this probability. We can break this down into two parts. Basically, what is the probability that x is greater than a and less than b? It's a probability that x is less than b minus probability that x is less than a. And knowing these two things, and knowing this inequality, we can redefine the probability that x is between a and b is simply the difference between CDF evaluated at b and CDF evaluated at a. So all of this is just, some arithmetics, but all of these properties are going to be also used throughout the whole course of, let's say, throughout the whole sequence of our statistics and econometrics subjects. And graphical representation of this. Look, if I have a graph of PDF, so this is a small f, and when I want to calculate the probability that my variable y is between a and b, so this is the area under the curve with these borders between a and b. So basically this object, this probability, this object, the integral of PDF, and this object, this gray area, are the same. And also this object. And look why. Because if this CDF is the area from minus infinity to b, and this is the area from minus infinity to a, when I take this area from minus infinity to b and subtract the area from, like this white area from minus infinity to a, I have exactly this gray area between them, between a and b. Yes, we must have some examples here. Yeah. Okay, so let's look at the example, and let's try to understand how to apply this. So before, in the previous example, we had this probability density function, 3/8 x squared. We know that this function is defined for values of x between 0 and 2, and then this PDF is 0 elsewhere. So we need to find these probabilities. Probability that x is between 1 and 2, including, and probability that x is between 1 and 2, not including. So strict inequality and weak inequality. So we have this first definition of this probability. So let's try to apply this. So this probability equals to the integral from 1 to 2. So let's go back here. So we have from A to B, right? So from between these two borders. So that's why I write this integral, and I integrate my probability density function. So this 3 over 8 x squared dx. So how do we do this integration? I take 3 over 8 out of the integral sign because it's just a constant, right? So it's here. And the integral of x squared is x cubed over 3 here. Now I evaluate this x cubed over 3 for values 2 and 1. So basically I do this. I plug 2 on the place of x. It's 8 over 3. And then I subtract x cubed over 3 evaluated at 1. So it's 1 over 3. Now it's 3 over 8 multiplied by 7 over 3. 3 and 3 cancels out, and I have 7 over 8. So that's simply how I can calculate the probability that for this random variable with this probability density function, so probability that my random variable is going to be between these two values is 7 over 8. Of course, you must be very careful when you calculate something yourself, and when you have this value greater than 1, you must be somehow suspicious that your result is not correct, because probability cannot be greater than 1. So that's at least this is one way how you can check yourself when you do something. If you have probability greater than 1 or negative probability, well, there is 100 chance that you are doing something wrong. Okay, and because x is a continuous, and we know that probability that x is exactly 1 and probability that x is exactly 2 are both 0. So that's why we can simply use this third property in order to claim that this probability that x is strictly greater than 1 and less than 2 equals to the probability that x is weakly greater than 1 and less than 2, and both probabilities are 7 over 8. No difference whether we include or not include. Okay, is this clear? How do we do this? It's kind of like, I think complicated thing is the calculation of integrals. So probably you already forgot about them. So now you need to remind yourself about integrals. But we are doing derivatives in microeconomics, so integral is just a reverse operation. Okay, and another new object that appears here is a quantile. Look, the quantile means the following. So let x denote any random variable. So we have just some random variable. It might be discrete, it might be continuous random variable, doesn't matter. And then we have some number p, and this p belongs to this interval between 0 and 1, not including. And then look, if you have some random variable, if you have some number p, which is between 0 and 1, then we call pth quantile of x. So it's kind of like 0.5 fifth quantile or 0.2nd quantile, something like that. We denote this as x tilde p. So this is the value such that CDF evaluated at this number equals exactly this small p. Or say differently, probability that random variable x is less than or equal to this number equals to p. So this is something like an inverse function to CDF. So before, when we calculated CDF, we plugged here some number, and then we calculated probability. Now we are doing the reverse thing. We ask, okay, what must be this number in order to get a given probability? If I want to get a probability of 0.5 or 0.1 or 0.3 or something like that. And that's exactly a quantile. And the concept of quantile is used in many different fields, from statistics, econometrics to financial management and risk management. So there is some example. Suppose we have a following CDF. So 0 for this part, x squared for this interval, and 1 for this interval. Now, if you want to find 0 0.3, 0 0.5, 0 0.75 quantiles, something like that, what should we do? We are looking for values of x such that this function equals to 0 0.3, 0 0.5, and 0 0.75, right? So we need to calculate something like this. So first of all, I know that this, if I plug x tilde p inside my CDF, I will get this x tilde p squared. It must be equal to number p. And then we can derive that x tilde p is just a square root of p. From here, I can derive what must be my x tilde p. So now, when I want to evaluate this quantile for 0.3, it's going to be the square root of 0.3, 0.55. So it means that if I plug 0.55 into this function, I will get probability 0.3 or 30%. The 0.5 quantile is the square root of 0.5, it's 0.707. Once again, if I plug 0.707 here, I will get 0.5 probability. And finally, this 0.75 quantile is 0.866. And so the graphical representation of a quantile is the following. So I specify a probability on my vertical axis, specify the probability here, and then I look for the associated value of x on the x-axis. So it's not like I take x and calculate y, I do the reverse thing. I specify probability, and then from this probability I move to the horizontal axis to find what x, or which x yields me exactly this probability. And there are some special cases of quantiles used in descriptive statistics, in inferential statistics, in many other ways. Median. So median is a 0.5 quantile. We also have special names for 1/4 and 3/4 quantiles. It's first and third quartiles. Why? Because they kind of cut the distribution of our random variable into 4 equal parts. So probability, so like one part with the probability 1/4, 0.25, another part with probability 1/4, 0.75, and what's inside between them is divided by this median into 2 equal parts as well. And the median is the second quartile. So if there is a first and third quartiles, there must be the second quartile, which is the median. And also we have this difference between third quartile and first quartile, which is called an interquartile range. So the interval where half of observations belongs to, let's say. So you have probably heard about the idea that when we measure an average salary, this is not a fair measurement of, let's say, welfare of people. Why? Because so sometimes people claim, well, median is the better measurement for the welfare of people. And why people claim this? Because look, median salary shows you the value of salary. So that's a quantile, right? So that's a value of your random variable, which splits the whole population of people into two equal parts. You have equal chance to pick a person with the salary higher than median or lower than median. But when you take an average salary, for example, the probability to pick a person with the salary lower than average is higher than the probability to pick a person with the salary higher than average. Why? So we will discuss this probably later in our course of mathematical statistics next semester. So there is the concept of skewness of the distribution. So when we have several people or several influential observations that somehow kind of take the average and pull the average towards them, then the average is not in the center of the distribution. The average is going to be shifted closer to the highest values. And that's why median divides you the whole population into two equal parts. But the average is going to be closer to those who are richer, and that's why more chances to select a person with a salary less than average. Okay. So with this, we finish our introduction into continuous random variables. You will have an exercise session. You will try to calculate quantiles. You will try to apply the ideas of PDF, CDF, and calculation of these probabilities. That random variable is between some interval. So any questions about this part of material? Clarifications, concerns, objectives? Okay, then we move to the next topic, which is called expected values. So now we have some knowledge about random variables. We also know that there is an object which is called a distribution of probability distribution of a random variable. And this probability distribution, as we just discussed, it might be represented with the help of graph, function, table, whatever. Now we want to have some special indicators to characterize this probability distribution. Especially for continuous random variables, it is crucial because we have a lot of possible values and it is kind of difficult to comprehend the whole distribution itself. So we use expected values in order to do this. So first, the definition. Definition for a discrete random variable, because we are going to have now a discussion for both types of variables, for discrete variables and for continuous variables. So if we have a discrete random variable and we have some probability mass function for this random variable px of x, so the expected value of x, we denote this expected value of e of x, is the following. So we take each value of x, each possible value of our discrete random variable, we multiply this by the associated probability, and then we sum over all of them. It's something like an average, weighted average, but we call this expected value because we are speaking about random variable. That's why we need to use some special terminology. But conceptually, this is the weighted average. If you remember mathematics, so you have weights, which are probabilities, and you have values of your random variable. And then you multiply each value by the respective weight, and then you sum over all of them. But don't call this weighted average, don't call this average at all. It's expected value. It has some special meaning in the theory of probability. And so we need to have this finite expected value. That's why this sum, if we take the absolute value of x, so this is just a formal condition, that this sum must be finite. And if the sum diverges, the expectation is undefined. We have some random variables for those with undefined expectation. So here is an example. We have a random variable x, and we have the following mass functions. So probability that x is 0 is 1 over 8, probability that x is 1 is 3 over 8, probability that x is 2 is 3 over 8, and probability that x is 3 is 1 over 8. And we need to find the expected value for this random variable. So look, now before I show you the solution, let's think. We have 1, 2, 3, 4 values that our random variable can take on. 0, 1, 2, and 3. And we have associated probabilities. 1 over 8, 3 over 8, 3 over 8, and 1 over 8. So what we should do? We should take each value of x, 0, 1, 2, and 3. We should multiply them by the respective probabilities, by this, and then we need to sum over them. So that's a simple thing. 0 times 1 over 8, plus 1 times 3 over 8, plus 2 times 3 over 8, plus 3 times 1 over 8, and we have 3 over 2. So as I said, this must remind you of weighted average, which you know from school. Weights and values of your variable. Now, if you got the idea that continuous random variable is the transformation of a discrete case when instead of summation sign we have an integral, then it's very simple to establish the definition for expected value of a continuous random variable. Because now for the continuous random variable, the expected value is this integral from minus infinity to plus infinity. So look, integral substitutes the summation sign here. Why from minus infinity to plus infinity? Because for continuous random variable, we have the whole range of real numbers as potential values. And one additional difference here is that instead of probability mass function p of x, I am using probability density function f of x. That's it. So that's the same thing, the same idea, with the slight transformation to the continuous case. And also we have the same condition of an existence, that this integral, when instead of x I'm taking the absolute value of x, must be finite. And if this integral diverges, then expectation is undefined. So for our course, this condition is just a technicality. We are not going to look at the cases when expectation does not exist. So don't worry. So this is just a technical necessary thing to complete the definition. So let's see on the example from the previous set of slides. If you have a continuous random variable with this PDF, this variable is defined on the range from 0 to 2, and then this is 0 elsewhere. We need to find an expectation. So once again, now we don't have a potential values of x, because x takes any value from minus infinity to plus infinity, but we kind of made this more precise from 0 to 2, because there is, so integral of 0 from minus infinity to 0 is just 0, right? So we don't need to write this down. So now I plug this function into the integral here, and then I need to evaluate this integral. It's here. So I take x, multiply this by PDF, 3 over 8x squared here, And then my borders of integration are from 0 to 2 here. So what I'm doing next, I take 3/8 out of the integral sign. I have x cubed inside, and the integral of x cubed is x to the power of 4/4. I evaluate this from 2 to 0, and it's here. It's so I also factor out this 1/4, so it's 3/8 times 4, it's 32 here. And then I multiply this by 2 to the power of 4 minus 0 to the power of 4, which is 2 to the power of 4 is 16, and 16 with 32 cancels, and I have 3/2 or 1.5. That's an expected value of random variable x with this density function. I think it's not that difficult, right? So you just know the definition of expected value, you apply this definition, and then you calculate what's that. So one step ahead. Suppose that we have some function of a random variable. So we have y and u random variable, which is the function of x. Any function, x squared, logarithm of x, x cubed, whatever. So now, how to calculate the expectation of this transformation? For the discrete case, we do the same, exactly the same thing. Now only one difference: instead of x itself, I am taking this function, this transformation of x. The rest is absolutely similar to the usual case of the calculation of expectations. And the same thing for the continuous case. If I have a transformation of my random variable, I plug this transformation inside the expectation, and I calculate expectation in the similar way. So which is very simple thing. If you transform your random variable somehow, the expectation of this transformation is calculated in the similar way as the expectation for the initial random variable, but you need to apply this transformation inside the expectation sign. Yeah, sorry for no, it's okay. Yeah, so there must be y here. Yes, there must be y, because now y is a new random variable. And this is an important thing that sometimes is confusing. So sometimes those who are not very familiar to the probability theory, they confuse these two things. Look, I'm looking for the expectation of g of x, right? So I'm looking for this. And this is not the same as this transformation of my initial expected value. So these two are different. We are looking for this, but don't confuse this with the reverse thing. So here is an example. Let's go back to the previous example about this discrete random variable. And now we define a transformation of this random variable. So suppose we have a new random variable y, and this y is x squared. So I transform my initial random variable into this. I need to calculate the expectation of my new random variable, because look, first of all, y is also random variable. Why? Because if x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 4. If x is 3, y is 9. Right? So y also takes 4 different values. Now, what is the probability that y is 9? It's the same as x is 3, right? So it's 1/8. Because if x is 3, y is going to be 3 squared, or 9, with the same probability, 1/8. So that's why calculation of this expectation is simply this. I first of all So expectation of y equals to the expectation of x squared. So this is g of x, right? G of x is x squared now. And now instead of x itself, I plug inside this transformation 0 squared, 1 squared, 2 squared, 3 squared. And I multiply this transformation by probabilities. And after the calculation, I have 3. And look, here expectation of x was 3 over 2. Here expectation of x squared is 3. And look at this, what I gave you here. So look, this is 3. But this is gonna be 3 over 2 squared, which is 9 over 4. So 3 is not equal to 9 over 4. That's what you need to understand. So you cannot simply take expectation of x, square this in order to get this value. No, they are not equal. So here is 3, and 3 is not equal to 9 over 4. And another example for the second variable, for the continuous case, the same thing. If I want to transform my random variable x in the following way, so it's x squared, and I want to calculate the expectation for the new variable for this transformation. Oops. So it's out of the page for some reason. I don't know why. But okay, so I think it's understandable, right? So I plug x squared inside my integral here. And then I do the same operations as before. So I take 3 over 8 out of the integral sign here. I take the integral of x to the power of 4, which is x to the power of 5 over 5. And then I calculate this, which is going to be 2.4. So I will try to correct the slides before uploading them to the Electronic University. Don't worry, you will get the correct version. So is this clear about expectation, about the expectation of transformation? Are there any questions about it? Okay, so now let's speak about some properties of these expectations. So suppose we have two constants, a and b, and we have two random variables, x and y. And then we will get the following results. So first of all, expectation of a constant is just a constant. Why? Because so constant has only one value with probability equals 1, right? So when you apply this definition of expectation to the constant, you have a multiplied by 1, which is just a. Nothing is needed to calculate. So now expectation of a random variable plus constant. What's that? It's expectation of a random variable plus this constant separately. So I don't give you proofs of this, but these proofs are kind of simple. If you think about this, and when x plus a is inside of this sum, then you can factor out this a, or you can break this sum into two parts. So this sum and a times probabilities, and then you will get a separately. That's why we have this property. So when I multiply random variable by some constant b, and I calculate the expectation of that, that's just this constant multiplied by the expectation. And property number 4, expectation of a sum of two random variables, x and y, is the sum of these expectations. sum of expectation x and expectation y. But be careful, product of two random variables and the expectation of product is not equal to the product of their expectations, never. So we will speak about this later when we will speak about joint distributions of random variables. So only this holds, only the expectation of a sum equals to the sum of expectations. So now some practical application of this. So suppose an investor plans to invest 1/4 of his capital into Amazon stocks with the annual expected return of 35%. So this is an expectation of a random variable of a return. And 3/4 of his capital into Tesla stocks with the annual expected return of 63%. So we have two expectations. We have two constants, 1/4, 3/4. So what is the expected return on his investment? So a return on the portfolio. So in order to calculate this, first of all, what's going to be the return on his portfolio? It's 1/4 return of Amazon plus 3/4 return on Tesla. And if you want to calculate this, we need to do the following steps. So first of all, expectation of this return on portfolio is the expectation of the following expression. So it's 1/4 multiplied by the return of Amazon plus 3/4 multiplied by the return on Tesla. So now, first step, I apply this property number 4. I break this expectation of a sum into the sum of two expectations here. So second step, I do this simultaneously here. I have expectation of a constant times a random variable, and I take this constant out of the expectation sign, and I have this 1/4 times expectation of Amazon plus 3/4 times expectation of Tesla. And finally, I am able to calculate the expected return on my portfolio, which is 56% in this case. So this is one of the classical examples that we use in finance, for example, where we use these properties, where we work with returns, stock returns as the random variables, and when we scale them by the weight of a stock into the portfolio. Another example that we can apply for finding an expectation of a binomial random variable. So suppose we wish to find the expectation of a binomial random variable. So, and if we want to do this straightforward, we will get something very nasty and weird. Look, we need to sum for all case from 0 to n of these things. So I hope that this is familiar to you. This is the BMF of a binomial random variable, and I multiply this by k. And now the question is, so go and find this sum. How to calculate this in general? It's difficult, right? So it's kind of very difficult to find. So what we can do, we can represent y as the sum of Bernoulli random variables x, which equal 1 or 0 depending on whether there is a success or failure in ith trial. So you remember that binomial distribution is based on the Bernoulli trials, 0, 1. And this variable is just a sum of these ones or zeros, right here. And then it becomes very simple, apparently. So instead of calculating this sum, which is very difficult to find, I need to calculate the expectation for this sum. And I know that expected value of x is what? So let me show you from the previous material. Where was it in the lecture number 5? Right here. I know that the expectation for Bernoulli random variable is just p, this, because I have, okay, probably it's here also. Yeah, so I know that expectation of xi of a Bernoulli random variable is 0 times 1 minus p plus 1 times p. Once again, why? Because my Bernoulli random variable is either 1 or 0. It's 1 with probability 1 minus, it's 1 with probability p and 0 with probability 1 minus p. So that's why expectation of a Bernoulli variable is simply p. And now I'm able to calculate this expectation of y, which is just an expectation of a sum of these variables. And this is the sum of expectations of x. And I know that each expectation of x equals to p. So I need to sum over p n times. And this is np. And look, instead of finding this difficult and kind of it's not even understandable how to find this sum, we transform the whole problem into the expectation of a sum of Bernoulli variables, which makes our life very simple. And now we know that expectation of a binomial random variable is np. That's simple. By the way, I didn't include in the previous material when we spoke about these distributions, I didn't include the calculation of expectations because we came to the expectations now. Basically, if you ever need something for your reference, you can simply Google this. So, for example, I don't know, Poisson distribution. Then you can go to Wikipedia, so it's okay. And in the Wikipedia, you will have all these things. So look, you have mean, which is exactly expected value in our case, which is lambda. So for Poisson distribution, we spoke that lambda is the mean or the average rate of occurrence. So, and that's also the expectation. Or here, you can find it. So if you need to know what is the expected value, how to calculate the expected value of some given distribution, so you can simply find Google it. It's available. Or like, I don't know, hypergeometric distribution. So the most exciting one. And here you will also get that mean equals to this n times k over n. It's the expected value. So for all of them, you have some given formula for expectation. No need to derive them. So internet is available, Wikipedia is available, so you can find all these expectations there. You just need to understand what are you looking for. Okay, so let's move one step ahead. Variance. So variance is the second most important, let's say, characteristic of a probability distribution. So there is a definition of a variance. So what is a variance? Variance is the expectation of this object. And here we have x, random variable, minus expectation of this random variable squared, provided this expectation exists, of course. So kind of we know how to calculate expected value. We know how to calculate expected value of some transformation. So now we apply these two things in order to calculate something which is called variance. So for a discrete case, if we denote the expectation of a random variable with this letter mu, it's also like a conventional way to to denote expectation with this small Greek letter mu. Then what we have, instead of expectation sign, I write down the way how I calculate this expectation. And that's x minus mu squared multiplied by the probabilities, by the respective probabilities. It's not difficult. It's not that difficult, you just need to see the similarity. So we started with the definition of expected value. And here I took x's and multiplied them by the respective probabilities. So now, instead of x's, I have these objects. I have this x minus mu squared, and I multiply them by the same probabilities. These are also numbers. So for a continuous case, I also substitute in the formula for an expectation, I substitute x with this x minus mu squared, and I get this. So basically these two formulas are formulas of expectations, where on the place of x I have this special object x minus mu squared. And one additional object, which is called the standard deviation. So the standard deviation is the square root of the variance. Simply this. When you know the variance, you are able to calculate the standard deviation. And from this moment, we will be using two types of notation. So one type of notation for expected value is just this e of x. Another way to represent expected value is mu. This letter mu. For variance, we are going to use either this var x or sigma squared. And for the standard deviation, sigma is usually used, so there is no kind of special way with Latin letters, so we can write something like SD or something like that. But usually, in almost all the cases, we are using this sigma. So now, examples. So this is the familiar random variable 0, 1, 2, 3 with the given probabilities. So now we need to calculate variance and the standard deviation of this random variable. So here is the way how we do this. So we know, first of all, let me remind you that we know the expectation of this random variable is where is that? It's here, 3/2. Okay, so now, knowing this expectation, I apply this formula. And I do the following. So I take each value of x, 0, 1, 2, and 3, and I subtract the expectation. I subtract 3/2. Here, 0 minus 3/2, 1 minus 3/2, 2 minus 3/2, 3 minus 3/2. I square these differences here, and I multiply each of those squared differences by the respective probabilities. 1/8, 3/8, 3/8, and 1/8. Here I have just new numbers. This, and this. 4 new numbers. And finally, my result is going to be 3/4. So after all these tedious calculations, I have 3/4. And this is my variance of this random variable. So now I have two numbers that characterize me the distribution of this random variable. So first number is the expected value, 3/2. And the second value is the variance, 3/4. And the standard deviation is the square root of 3/4, which is, I think you can calculate, but I didn't. I just left it as this. And for the continuous case, this is the familiar continuous random variable. So now if we want to calculate variance and the standard deviation, we apply the same procedure. I plug this So it's x minus expectation squared multiplied by PDF. And then I need to integrate it. So this is somehow kind of long way to do, because I first factor out the 3/8 of the integral sign. Then I square this. I write this as in the following way. So it's x squared minus 3x plus 9/4 multiplied by x squared. Then I need to break down this integral into the sum of integrals, but I kind of omitted this part. So I just integrate each part separately. So x fourth is the integral of x to the power of 4 is x to the power of 5 over 5. So here it's 3x cubed. Integral of this is 3x fourth over 4. And then it's 9/4 x squared, which is 9/12 x cubed. And then after the evaluation of all these things, I have 3/20. So this is just an arithmetics here. So the most important thing is this, to plug instead of x, to plug this object, and this to calculate properly the integral. So all the rest is just arithmetics. And yeah, and sigma is somewhere there, so it's square root of 3/20. So 3 more slides and 5 minutes left. So basically we also have some properties of variance. So now please be careful, because properties of variance is very easy to confuse with the properties of expected value, but they're a bit different. First of all, variance of a constant is 0. Why? Expected value of a constant is it's constant. But now if you go to the definition of variance, so now you have a minus a. What is the expectation of a minus a? It's 0, right? Because it's expectation of 0. And squaring doesn't make any difference. So that's why the variance of a constant is 0. There is no variance in a constant. So now variance of a constant plus x is just a variance of x, a variance of a random variable. Because addition of a constant doesn't change anything with respect to the variation in the random variable. So now variance of bx constant times a random variable is b squared variance of x here. And very important thing is that generally variance of a sum is not equal to the sum of variances. Don't confuse this thing with expectations, please. So for the expectation, this holds, right? So expectation of a sum is equal to the sum of expectations. For variances, generally it doesn't hold. How to deal with this? That's a material for our next classes, when we will speak about joint distribution of random variables. So now, please remember this. And there is another way to calculate variance. We can calculate the same thing, the same variance, applying this formula. So it's expectation of x squared minus expectation squared. That's what I showed you, that there is no, they are not equal to each other. So expectation of a transformation and transformation of an expectation, they are not equal. So now we apply both. So there is a simple way to prove this. I will skip this proof. So if you are interested, you can look at this. It's kind of very simple way how to get from here to here. But we will have only 2 minutes, so let me finish with the example. So here is an example how we are able to do this. We already did the calculation of ex squared for the discrete variable. It was 3. We know the expectation of x is 3/2. So now variance is simply 3 ex squared minus 3/2 squared, which is 9/4. And we have 3/4. which is exactly the same variance as we calculated here. Exactly the same number. Just another way to do the same thing. And for the second variance, for the second random variable, sorry, it's expectation of x squared is 2.4, expectation of x itself is 1.5, so now I make this 2.4 minus 1.5 squared, and I have 3/20, the same result as here, 3/20. So I think that this way for calculation of a variance is simpler, right? Because you don't need to do all these long calculations as here. So on the exercise session, you will see both approaches, and then you will be free to choose which approach is simpler for you. I mean, so both of them are possible. Okay, so here we have two inequalities. I will comment on these inequalities on the next class. We will start with these inequalities, so don't worry, they are kind of useful, but I think for today there is enough of a new information. On Saturday you will have an exercise session. You will go through all these topics through the expected values, variance, and also the operations with the continuous random variables. And then you will have home assignments. So I think, yeah, after the weekend you will get two home assignments. One is going to be about continuous random variables, and another is about expected values. So check the course page after this weekend. Okay, any questions? Okay, so then thanks for your participation. See you in 15 minutes for microeconomics.